In this video, we're going to look at equations of planes. Any two non-parallel vectors, A and B, are coplanar, so we see them right here, and define a plane. Any other vector V in the same plane can be written as some sort of combination of A and B. So any other vector that exists in this plane is just a matter of rearranging A and B and multiplying them by different scalar values, and then we can get any vector in that plane. So V is just A plus B, but A and B are multiplied by some scalar values S and T. A and B are called your basis vectors for the plane. Every plane has an infinite number of pairs of basis vectors, so any pair of two non-coincident vectors in the plane. The vector of equation of a plane is a general expression for the position vector OP from the origin to any point on the plane, right? So it will create just like a vector equation of a line that points from the origin to any point on the line. The vector equation of a plane will go from the origin to any point on the plane. For any point P on the plane, the position vector can be expressed as the sum of the two position vectors, and I'll show the position vectors right here. You can already see one position vector, this one right here, that's sitting on the plane. From here to here is another position vector. Right, there you go, that's your B, okay? So OP can be expressed as the sum of the position vectors from the origin to a specific point in the plane, and then the vector in the plane from P to P naught as well, right? So this is similar to how we wrote the vector equations for lines. But every vector in the plane, P naught P, can be written as a combination of the two basis vectors A and B. So this right here is going to be, this is your vector equation of the plane. So OP is OP naught, right, which is your position vector to a point on the plane plus S times A plus T times B, where A and B are your basis vectors that define the plane. Okay, so it says find vector and parametric equations for the plane containing these points, 1, 6, 0, -3, 5, -4, and 6, -3, and note that 3 points are required to define a plane. So what I'm going to do is, if I have 3 points on a plane, then I can just kind of sketch this out for you right here. This is like my plane right here, and if I have 3 points, then I can create basis vectors by joining the points, and then I have a point on the plane, right? So two basis vectors and a point on the plane will create an equation of a plane. So what I'm going to do is I'm going to say I'm going to find my basis vector A. Okay, so I'll find my basis vector A. So A is equal to P1, P2. Okay, so basis vector A, if I do P1, P2, that is -3 minus 1, 5 minus 6, -4 minus 0. Again, I'm just subtracting the position vectors to those points. Okay, so A is -4, -1, -4, and I can just take the vector in the opposite direction. It's still going to lie on the same plane, so I could say or also 4, 1, 4. That doesn't really matter. Okay, B is equal to P1, P3. That's my other basis vector, right? And so that's equal to 6 minus 1, -1 minus 6, 3 minus 0, and then I get 5, -7, and 3. And so therefore the vector equation is going to be, so I take a point on the plane, 1, 6, 0. I could have used any of these points, by the way. And now I just add my basis vectors. So S times A, so -4, -1, -4, right? Plus T, and then 5, -7, and 3, where S and T are element of real numbers. So that's my, excuse me, that's my vector equation, and then my parametric equations are x is equal to 1 plus negative 4s or minus 4s plus 5t. Y is equal to 6 minus s minus 7t. And z is equal to negative 4s plus 3t. Note that we don't have a first constant because it's 0. Okay, moving right along to the next example. There's only 3 examples in this lesson. Okay, find a vector equation for the plane combining the z-axis and the point 2, negative 3, 10. Well, if I'm using the z-axis, then I already have one of the basis vectors. And one of the basis vectors that I can use is equal to just the direction vector along the z-axis, which is 0, 0, 1. Okay, and if I have a point on the plane, I can create another basis vector by saying, okay, another point on the plane if the plane combines the z-axis, then that means it also goes through, the plane also goes through the origin. So the origin sits on the plane. So we'll write that right there. Origin sits on the plane since the z-axis is on the plane. Okay, so what I'll do is I'll find my basis vectors. Okay, so I'll just write over here, basis vectors. Okay, again, I already have one of the basis vectors. I'm just going to use the unit vector in the z direction, 0, 0, 1. And then my other basis vector is going to be from the origin to point 1. And that's really just equal to 2, negative 3, and 10, right? Because if I was to do the origin to this point, then final minus initial, well, 2 minus 0, negative 3 minus 0, 10 minus 0, okay, yeah, it's the same. All right, so I've got my 2 basis vectors, and now I need to just find my vector equation, and this should be fairly straightforward. I take a point on the plane, well, I'm given 1 right there, that's fine, 2, negative 3, 10, and then plus the first basis vector, 0, 0, 1, plus t, 2, negative 3, 10. Okay. I could also have used this point right here, and so instead of this OP naught, 2, negative 3, 10, I could have just written 0, 0, 0, or omitted it entirely and just had these 2 basis vectors for that plane. Okay, the final example. Determine whether the point P1, negative 2, 4, 1 lies in the plane OP. So 2, 3, 4 plus S, 1, negative 3, 7 plus T, negative 2, 1, 3. Okay, so what I'm going to do here is the first method that I could use. Okay, there's 2 methods that I'm going to do right here. So let's try, I'm giving you the heads up, try and write small because we're going to try and fit 2 methods of doing this. All right, so here's method 1. Okay, and again, I'm also going to try and write pretty small. So what I can do is I can come up with the parametric equations for this plane. X is equal to 2 plus s minus 2t, y is equal to 3 minus 3s plus t, and z is equal to 4 plus 7s plus 3t. And I'm trying to find if this point lies on this plane. So what I can do is I can sub in the values of negative 2 and 4 for x and y, get my s and t values, and see if using that s and t value will generate 1 for z. And if it does, then the point's on the plane, and if it doesn't, the point is not on the plane. So here I can do set x is equal to negative 2 and y is equal to 4. So I'm setting that up, and I get negative 2 is equal to 2 plus s minus 2t. 4 is equal to 3 minus 3s plus t. So the issue with these 2 equations is I can't eliminate a variable as is currently. What I can do is I can take my second equation here, okay, and I can multiply my second equation by 2. And so in so doing, I get negative 2 is equal to 2 plus s minus 2t. Again, I'm mathematically allowed to do this because I'm augmenting everything by a factor of 2. And so then I get 8 is equal to 6 minus 6s plus 2t. And now you can see I have opposite signs in the not in the numerator, in the equation above and in the equation below. So I can add these two equations right here. And I get 6 is equal to 8 minus 5s, and 2 over 5 is equal to s. Well, subbing that back, this s value back into one of these equations will give me t. Therefore, t is equal to 11 over 5, right? And you can just do that by taking this 2 over 5, for example, and subbing it into equation 2, or take 2 over 5 and sub it into equation 1, and you'll find you get t is equal to 11 over 5. So now I'm going to take this s, and I'm going to take this t, and I'm going to use that for my z. So sub 2 over 5 equals s, and t is equal to 11 over 5 for z. Okay, and so then I'll have z is equal to 4 plus 7, 2 over 5, plus 3, 11 over 5. And so z is equal to 67 over 5, right? Which obviously does not equal to the 1 that we were expecting to get. So 67 over 5 does not equal to 1, and therefore P1 is not on the plane. So I would say that is probably the more intuitive way of going about this, because this is a method that we've seen before. But here's another method that you can do, because we're dealing with planes, and we've also seen something like this before. Well, method 2 is we're going to make a vector, okay, in that plane, okay? And so we're going to make right here, I'll show you right here, we're going to say make P1, P0, right? So we're going to take this point on the plane, and we're going to join it and make a vector with this point right here. So P1, P0. And then we're also going to find n, the normal vector of the plane, which is equal to A cross B, okay? And if P1 is on the plane, then this right here, P1, P0, dot the n vector should be equal to 0, okay? So if you think about this right here, okay, this is your plane, all right? If you have A and B here, and you form a normal vector on that plane, okay? If you have another vector, so the P0 and then P1, if P1 is on that plane, then it should also be orthogonal or perpendicular to the normal vector. So we find the normal vector by taking A cross B, and we're going to check to see if this normal vector is perpendicular to P0, P1, and if it is, then P1 lies on the plane, and if it's not, then P1 does not lie on the plane. Okay, so let's find P1, P0 first. P1, P0 is equal to 2 minus negative 2, 3 minus 4, 4 minus 1, and so that's equal to 4, negative 1, and 3. Okay, and my normal vector is going to be equal to just the cross of A and B. So do your cross product somewhere else, right, on a scrap piece of paper, and you'll find that the cross product is equal to negative 16, negative 17, negative 5. Okay, so again, if P1 is in the plane, then the dot product of P1, P0, and n should be equal to 0. We should have this situation if P1 is in the plane. Okay, we've already evaluated that P1 is not in the plane, so we should expect this to not equal to 0, but let's see what happens anyway. Okay, so we'll check, and this also, by the way, this is called the triple scalar product, right? Because P1, P0, sorry, let me just do this right here. Dot the n vector, well, the n vector is just A cross B, right? That's your n vector, is equal to, this right here is called your triple scalar product. So we'll see if the triple scalar product is equal to 0. And by the way, this is something in the algebraic vectors unit. So for negative 1, 3, that's my P1, P0, dot product negative 16 and negative 17, negative 5 is equal to negative 64 plus 17 minus 15 is equal to negative 62. Negative 62 does not equal to 0, therefore P1 is not in the plane. Okay, so that's it for this lesson. Thanks for watching.